Hello everyone, we are with Guangdong Provincial Key Laboratory of Millimeter Wave and Terahertz, South China University of Technology. It is our pleasure to have the opportunity to share our work, cross-band decoupling method for dual-band, aperture-shared antenna array using Metasurface. Nowadays, 2G, 3G, 4G, and 5G base stations coexist. However, the space for base station antenna array is very limited. Therefore, aperture-shared antenna array is proposed. The main challenges in designing multi-band, aperture-shared antennas array including impedance mismatching, port-to-port isolation deteriorated, radiation pattern deteriorated, realized gain decreased and so on. This communication presents a method of using Metasurface to suppress the cross-band interference between low-band and high-band antennas for the design of a dual-band aperture-shared antenna array. With an interleaved layout, the proposed antenna array is composed of a low-band antenna and 4 high-band antennas. The proposed Metasurface consists of 5 square loop-shaped unit cells, placed above the low-band antenna. 4 10-ohm resistors are loaded symmetrically on the 4 sides of each loop unit cell to achieve the absorption function. The main novelty is that the Metasurface absorbs and cancels the high-band currents induced on the low-band antenna, and the mutual coupling between the antennas can be reduced. It can be seen that the Metasurface has band stop and absorption characteristics in high band, and its absorption increases with or increase. When the Metasurface loaded on above the low-band antenna, the low-band antenna has a higher out-of-band suppression level of over 17 dB and 3.3 to 3.8 GHz. The reason why the proposed Metasurface reduces the out-of-band gain of the low-band antenna can be explained by current distribution. At 3.6 GHz, the current direction on the loop unit cells of the Metasurface is always opposite to that on the dipole. These two currents cancel each other. At 1.7 GHz, the current direction on the loops is consistent with that of the dipole. The current on the dipole and the square loops are in phase and superposed. Therefore, the proposed Metasurface can achieve the out-of-band suppression and enhance the in-band radiation. To verify the decoupling effect of the Metasurface, a comparative study is made. Compared with case without the Metasurface, the isolation between port 1 and port 3 of the proposed antenna array is improved by more than 30 dB at 3.5 GHz. The proposed dual-band aperture-shared antenna array is fabricated and measured. The simulated and measured bandwidths of all the low-band and high-band antennas are wide enough to cover 1.7 to 2.7 GHz and 3.3 to 3.8 GHz. The cross-band, in-band and polarization coupling keeps a low level in the whole operating band. The measured radiation pattern and realized gain are basically consistent with the simulated results. With a small FR, the proposed dual-band aperture-shared antenna has higher cross-band isolation and larger operating bandwidth. Thank you.